Okay, so in this video we're going to be going over how to communicate from your board back to your computer using the SCI pins using the UART protocol. So in the last video we learned how to communicate to the board using our USB cable and the debugger, as well as to actually impact things on the board with flashing those lights. So what we're going to do now is, obviously we want to as well be able to pass information from the board back to the computer so we can find out what's going on internally. So we accomplished that using two pieces of hardware other than the board. The first is what is known as a breakout board, which you can see here. So this will be provided to you by the club. If you don't have one, make sure you get your hands on one here because this is necessary for this task. So essentially what this is just a little board that plugs in via USB right here. So this goes into your USB port, and then it breaks it out into multiple different pins you can utilize. So there's 5 on top and 5 on the bottom. You can't see in this picture, but fortunately the 3 we're going to be using for today are on this. What we do then is we plug wires into these different little inputs, the female connectors, and then we can plug those wires onto the board itself, onto those headers, which you can see on the board here. So it's essentially these certain pins here are going to connect into certain pins here. So the 3 we're going to be using today are known as TX, ground, and RX. So we're using the UART protocol, and essentially what that necessitates is a single bus, data bus, which is the wire itself, to pass on information through a receiving pin and a transmitting pin. So those are the 2 major connections you need to use for this SCI setup, as well as a grounding pin for obvious reasons. So what we're going to do here just quickly is we're going to reference our TI data sheet, and we're going to see where exactly those pins are on the board so we can connect them up properly. So first we'll start with ground. If we look at, I believe it's J2, J3 header 2, you'll notice that that's our ground one. So what we're going to want to do then is we're going to want to connect this ground into the pin, the ground pin, which is header J3 pin 2, which is labeled on the board if you're unclear. Otherwise, just feel free to look at the diagrams and their literature here. So you're going to connect ground to ground, obviously. The next one we'll do here is, let's take a look at TX. So we want to connect TX. Now, your initial strategy may be to connect TX to TX, but actually what you want to do is you want to connect TX to RX, so transmitter to receiver. So the reason for that is obviously these are this SCI connection is a two-way thing where you can receive or pass information from one device to the other. So naturally you're going to want the ability to connect the transmitter, so the thing sending the information, to the receiver of the other device, because if you have 2 transmitters connected, they're just going to be firing information at each other and there's not going to be any reading. And if you have 2 receivers, there's no information in the first place. So you're going to connect the TX on your breakout board to the RX pin, which is SCI RX right here on your board itself. So J2, 3, and then you're going to do the exact same thing, just vice versa for RX. So the SCI RX on this board here is going to go into the SCI TX on your dev board. You'll notice there's a whole bunch of different listed things. A lot of them you might not be familiar with, which is fine. This is that pin multiplexing stuff I mentioned about before. So essentially what this is a specific pin's ability to handle multiple different protocols that you might want to use to pass information. So what we're going to do now is we're going to go into Halcogen and tell Halcogen, okay, of these 3 options that this pin is able to use, this is the specific one we want to use, which in this case is SCI. So now that you've set up the hardware itself, so again, just to reiterate, you have those 3 wires coming from the breakout board, so TX, RX, and ground, into TX, RX, and ground in the board, as well as the USB cable from your computer to the board itself, so you're able to actually pass information in terms of flashing the code to start, as well as power the board. Those are kind of the 4 connections you should be establishing right now. We're going to go into Halcogen and we're going to make some changes to the code. So what you're looking at here is the original Halcogen file from the previous GIO video. We're just going to be building on top of the stuff we have, and this will be a nice showcase of the nicety that Halcogen has, where you can make changes in the background to the abstraction layer and then go back into your original code without things being changed. So we're going to go through those 3 steps I mentioned in the first video to establish these communications. If anything I'm saying right now is a little too fast, do feel free to go back to the GIO video as I go through Halcogen usage a little more in depth and a little more slowly if this is still too new for you. So yeah, we're going to start with our SCI setup now, as that is what we're going to be using to pass information along. So again, first up, driver enable. We're going to both enable the SCI and the SCI2, and with that, we've enabled the drivers successfully, so we're good to go for that. The next thing we're going to want to do is let's head into SCI itself. So within SCI, we need to enable TX or RX, and off the top of my head, I'm not remembering which of the two it is. So what I'm going to do here is I'm going to go take a look at another pre-established program that utilizes the same thing. I'm going to click yes to save that. I'm just opening this new project here just for a second, just for reference. Go to SCI Global. Okay, so we want to enable RX. So now I'm just going to head back to the project we're currently working on. Okay, we're going to enable RX. Go. And SCI RX. So on both SCI 1 and SCI 2 pins. The current setup we're using only uses the SCI pin, but typically we like to set both of them up ahead of time just in case we end up wanting to use both. It's not necessary, but it's just something we tend to do just out of habit. So now we've set up SCI, the actual SCI settings, and the driver has been enabled. Now, unlike GIO, SCI has a little more complexity because of that pin multiplexing I just showed you. So what we're going to do is we're going to head over into PinMux up here. And what we're going to do is we're going to go down and find that specific pin we were looking at on the TI diagram where it had the potential options. So as you can see, it is pin number 39 and 38. We're going to scroll down to pins 39 and 38 here. So right here. So as you can see, here are all those options it was listing. So you have the HET, SCI, and then ETP. So essentially what this is saying, again, is that this pin is capable of utilizing all of these protocols, and it just needs to know which one you want to use. Obviously, for our purposes, we're trying to use SCI, RX, and TX, so we're going to enable those. So those are the 3 steps we're going to need to do in Halcogen itself to set up SCI. So again, I'm going to save the project, and what I'm going to do is I'm going to regenerate the code. So again, you'll see lots of activity down here. All those background files we looked at in the first video, so the headers and the .c files have been regenerated now. But the great thing is when we go to Halcogen again, we're going to get a little notice saying that your file has been changed because of those changes to the Halcogen. We're going to click yes because we want it to replace the things. But the great thing here now is that as we look through our code, all those original things that we wrote in between the user code begin 1, user code end, are already, or pardon me, have remained. They haven't been deleted despite the regeneration. So again, that's why it's so critical to write stuff within these comments. So now let's get into the actual code we're going to be doing today, which is nice and simple, fortunately, because of FreeRTOS's built-in functions. So we're just going to need to use one of the functions that FreeRTOS is using to pass information from our board to the computer. So again, good first step is always to include the library you're going to need to use this. In this case, we're using sci.h, so I've already gone ahead and put this in. So as you recall, last time we used gio.h, this time we're just using sci, because sci is the protocol, or the pin, sorry, we're going to use. Now let's head into main and actually write some useful code that we're going to utilize for the video project. So again, what I've done here is I've just copied and pasted some previously existing code that accomplishes what we're trying to do today. And I'm just going to walk you through step by step what this code means. So ignoring this highlighted line here, this is the code that was already done, which is the code that flashes the light and then this little delay loop, because at this point we have not put this in a scheduler. So we're just wasting the computer's time so the light flashes at a slightly slower rate that we can actually see. So what we're going to do now is let's take a look at the code we actually use to send information from the board to the computer. So one of the first confusing parts is whether you should use send or receive, which are both FreeRTOS functions that are built in for our usage. The best way I can explain this is think of all the code you're writing is going onto the board itself. So all the code in terms of sending and receiving should be written from the perspective of the board. So what I mean from that is if you're looking from the board, you are sending information to the computer. So that's why we're using send rather than receive. Moving on from that, send, as you can see, takes 3 parameters, much like GIO. The first one is, similarly again, is the SCI register itself. So because SCI SCI is a much more information intense protocol. It's probably a bad word. It allows for more. Essentially, there's more bits in it. It uses an entire register to pass information along. That's why we pass strings through it and things like that. So because of that, we don't have quite as much specificity in terms of selecting a specific bit to send information over here like we do in GIO. So we selected the port and then a specific bit. With SCI, we just select an entire register and that's it, because it needs that entire register to do whatever it's doing with the SCI protocol. So the first thing we're going to do again is we're going to set up the SCI register. So for your LS12 board, it's going to be SCI reg. If you are on an LC43 board, which is the older development board, I believe it is SCI reg 1. So this varies from board to board. It's just the terminology associated with this specific board. So different ones have different built-in register names. That's all it is. It's not changing what you're doing. It's just what they just changed name from board to board. If you're unsure of what it is, look it up on Google. If you're struggling there, take a look within this sci.c file, as the different registers will actually be listed within that. So you can take a look and see what you can potentially access for usage. So second parameter is actually the length of the string we're going to be sending via SCI. So just to clarify, this is not referring to a specific bit like GIO was. This is the length of the string, because again, SCI uses the entire register, so we're not specifying any bits. So in this case, I've set it to be a 20 bit string. And now what I'm going to do is I'm going to actually input the string itself. So what we do with the UVST here is we typecast our strings to unsigned chars for data handling and information purposes, which you'll get a little more accustomed with later. For now, just make a habit of always using unsigned char stars as our typecast for the specific string. And then I've just put in a little dummy string here. So I said UVST is number 1, bunch of exclamation points, nice little tab space, and a new paragraph. So that's just the string we're going to be generating from the board and sending to the computer itself. So that's the extent of the code, fortunately. It's just a nice simple operation. I'm going to delete, I don't know why I have 2 return zeros in here. I'm just going to delete one. So what we're going to do now is we're just going to save this code. We're going to build it. Probably going to get just one warning which says we're not going to reach the return 0, which is expected because obviously we have an infinite while loop here with no breaks, so that will never be reached. Yeah, there's that warning. Great. Okay, so no issues with this code. Again, feel free to pause this and just copy and paste, make it your own string, mess around with it. Also, feel free to take a look in the C file, see what other registers you can send. So the reason I checked SCI1 and SCI2 in Halcogen, back here, back in the driver enable. So the SCI1 and the SCI2, which are not checked anymore. I guess I wasn't careful with my save. It's not going to be a problem for us because SCI1 is checked, which is what this is using. But let's say, for argument's sake, you wanted to just use the second SCI register that's available to you. You'd want to enable that SCI2 driver and then send this to, I believe it is SCI reg 2. If I'm wrong, just take a look in the sci.c file and you'll see the different SCI registers listed. But I believe it's SCI reg 2. So we've built the code, we've saved the code. Now let's debug it. This always takes a bit of a process because by standard, what your Code Composer Studio is going to do is it's going to actually wipe the entire flash on your board and then reflash the code to it, which is a little bit of a time-consuming process. Okay, so it's completely debugged. What I'm going to do now is, before I press play, I'm just going to explain how we access this information that's coming to the board. So your computer has different communications ports that are used for exactly what it sounds like, internal communications, or incoming communications, I should say. So what we're going to do here is, before you set up your code, or pardon me, before you start running your code, we're going to go into is the Windows Device Manager. So if you haven't used this before, this is essentially just a big list of all the I/O within your computer itself. And what we're going to go look at is ports right here, so COM ports. So this is the entry point of the connection between your dev board and your computer. So the USB that you've plugged in via the breakout board is going to be recognized as a COM port, communications port, that then your computer will read information from. So as you can see here, I have 3 listed, and these are all actually from the board. So I'm just going to explain them top to bottom. So the reason we have you guys setting up this external USB to UART breakout board is because our actual OBCs don't have that nice little internal debugger where we can just plug USB in and use everything for that. We need to be using these external hardware pieces that plug onto the OBC because of the fact that we don't have necessarily all those niceties inside of our board. So what we're going to see here are 2 XDS 110 ports and then this USB serial port. So going top to bottom here, USB serial port, so in this case it's COM5. Your computer may say something different. That's totally fine. You don't need to worry about that. The important part is just that you note whatever COM port it is plugged into. So for me it's USB serial port, which is COM5. So that is the COM port for your actual breakout board. So that's the one we want to care about today because of the fact that that's where the information is coming through. The other 2 are XDS 110 COM7 and COM6. So COM7 is the receiving information, so the UART receive. So when you just plug your board in on its own without this fancy breakout board, that's how your computer is going to receive information through the USB stick. And this is how it's going to send information, so COM6 and COM7. So again, don't need to worry about those today. Those are just the ones from your USB connection. This is the one we care about because that's that little breakout board we've plugged in. So COM5 is what we're looking for here. So what we're going to do now, we're going to start running our code. I'm actually going to close this down just for demonstration's sake. We're going to start running our code, and again, provided you're using the same base code that you did for your GIO, that light should start flashing again as expected. But now what we're going to do is we're going to go one step further and get that information that it's sending. So what we're going to do here is we're going to go into View. We're going to go into Terminal. So Terminal is essentially our central location for all those COM ports. So this is what we'll use to view the information coming into a specific COM port or something like that. So you'll notice here, terminal, we have a whole bunch of different options. So you have a git bash, your local terminal, SSH. So just a bunch of different ways to receive information, and then this just essentially just displays it in plain text. So in this case, we're using serial terminal because as you noticed, so I closed it down. Let me open it up. You'll notice within ports COM, it's a serial port, so we're using a serial connection. So we're going to choose a serial terminal, and the nice thing with CCS is it does detect what ones are active. In this case, it notices that all 3, so the USB ones and then your COM5 USB serial 1 is active. Don't mess around with the baud rate or the data bits, parity bits, anything like that. We just use the standard stuff for this demonstration, so you don't need to worry about any of these settings. Just make sure it's set to that COM port that aligns with your breakout board. Your encoding, use UTF-8, and you're good to go. So now what we're going to do is we're just going to press OK. What we should see down here is this is going to start populating. Looks like it's spazzing out right now, and that's just because it's constantly firing those strings over and over and over in that while loop. The reason we did that is just so it's obvious that it's active and when it's not. So for instance, if I were to unplug the breakout board, which I'm going to do right now here, you'll see on the screen that it's just going to stop sending that information because that's where the information is coming through. Now if I haven't unplugged the USB, so the board is still powered and everything, and the code is still running. I'm going to plug the breakout board back in, and we should, maybe I need to boot it up again. I'm going to eat my words here. Let's just go, sometimes you need to reopen the terminal again just to start getting it to read information from the board again. Yeah, there we go. So I've unplugged the breakout board, plugged it back in, and then just kind of restarted the terminal. You could do that a little more smoothly than closing down the whole thing and opening it again. I believe if I just press the X, yeah, that'll keep the terminal open, and then I can reopen it. So you're going to see the information start flowing again. So that kind of proves the fact that the information is coming through that breakout board itself rather than the USB. So at this point now we're capable of flashing code to the board, utilizing those internal LEDs, and then firing information back to our computer through an external source. In our next video, we're going to be going over how to schedule all these different interfacing things, because ultimately it's great that you can interface with the hardware, but obviously we want to start to work with that information and use it in useful ways within our software. So that's what we're going to be covering in our next video.